Okay, let's see what we got for your Unit 4 exam. The minimum and maximum mass for stars. Actually, I went ahead and brought in, you might recognize for those of you who were there, that this is the whiteboard. It's kind of small. I think put it up on Twitter too. But stars can have, they have to have at least 0.08 solar masses, and then if they're less than that, they don't have enough to begin nuclear fusion in their cores. And if they're greater than 100 times the mass of our sun, then they're just too big. They don't kind of settle in. Stars can be as massive as 150 times the mass of our sun. So either 100, 150 times the mass of our sun is kind of the upper limit. There you go. That's that one. So there's my HR diagram. Of course, along the x-axis we have temperature, and along the y-axis we have luminosity. MS stands for main sequence. You can kind of see that slanty line there. So these x's then represent stars on the main sequence. And we said that actually Hertzsprung and Russell found that they can put a group of stars up and they get these kind of different clusters. And so actually if you have a bunch of stars that are born about the same time, they create this what's called a turnoff point. And you can kind of see it there. So of course as they turn off the main sequence, they have aged to the point where they are no longer have, they ran out of hydrogen in their core. Now they just have helium. So the point here is the HR diagram kind of shows the aging of a star. Stellar evolution, the aging of a star. Oh yeah, I have a few more things on here. So it leaves the main sequence and it goes in the giant stage. Now, if it's a massive star and that the threshold's going to be actually 8 times the mass of our sun or greater, it's going to go supernova, going to blow up. You can kind of see there in the upper right-hand corner with a couple arrows. It's going to either be turn into a neutron star or a black hole. And then if it's lower than 8 solar masses, WD stands for white dwarfs in the lower, it used to be the lower left-hand corner. So that's the stellar evolution HR diagram. We definitely kind of talked about the different ways a star lives its life. So when a star leaves the main sequence, like I said, it has done what our sun is doing, take hydrogen plus hydrogen to form helium, and it basically ran out of hydrogen in its core to do that with. So it leaves the main sequence. So red giant, think of those, they could be supergiant, red giant. They are a swollen star that has left the main sequence. Brown dwarf, we saw this in the video that we watched. Actually, that's the failed star. Brown dwarf is not quite 0.08 solar masses, so it doesn't have enough mass to begin to create the pressure and the temperatures needed in its core to begin nuclear fusion. See, planetary nebula, that is actually after think of it like this, like the star has actually even left the red giant stage, and it's kind of the matter and its swollen part is kind of lifted off and is formed this kind of cocoon around it called a planetary nebula. They are beautiful, right? So the center of a planetary nebula, you should find a white dwarf. White dwarf is a retired star. It's a low mass star. So again, we're talking 8 solar masses or less are going to end their lives as white dwarfs. We did talk about those kind of crazy red dwarfs, the 0.08 to 0.4 solar masses or red dwarfs. But so in this chapter, the supernova that they talked about was the stellar, the stellar was the one where the massive star blows up. So that is, of course, we talked about that in the next chapter as being the type 2 supernova. And the threshold for that is it has to be 8 solar masses or greater. And the core, the thing that's left over after the explosion, well, it depends on the mass of the star that blew up. From 8 to 25 solar masses, the thing that's going to be left is that little nubbin is going to be a neutron star. From 25 solar masses up to 100 or 150 solar masses, the star blew up. Now that's solar masses as it was a main sequence star. In that case, you're going to get a black hole. All right, on to chapter 14. So it's called the Chandrasekhar limit. a white dwarf, in order to be kind of what we call normal matter, where the electrons kind of separate the different atoms, electron degeneracy, the white dwarf cannot exceed 1.4 solar masses. And then do you remember how the volume was related to the mass? It's kind of backwards. So basically, the more massive it is, it has more gravity and it pulls the volume smaller. So it sounds a little backwards. The more massive it is, the smaller the volume is going to be. So for the nova, I drew a little picture up there to kind of show you that most stars actually, remember, has a companion. And if we have a retired star, which is a white dwarf, and if it has a companion that's a swollen red giant of sorts, then that hydrogen, and I have it in green here, can come from the companion that's still alive and dump on the retired star. And with a nova, remember, it's kind of a gentle explosion compared to a supernova, is the way I think of it. So what happens then is kind of on the shell of the retired star, it gets more and more hydrogen, and actually it's pulled in pretty tightly, and it creates the correct pressure to go ahead, I guess, and temperature to begin nuclear fusion. But it's like a runaway, just kind of a quick, like blowing off a blanket. So nova events are like blowing off a blanket, and they can repeat themselves. A pulsar is pretty cool. Pretty cool. That's those little green men signals. So a pulsar is actually a signal showing the presence of a neutron star, and that was that lighthouse sort of model. I don't know if you remember, where there was a crazy magnetic field that extends from the neutron star, and it kind of energy kind of squirts out of the kind of the polar regions. So as it swings around, it goes blip, 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 blip. That's a pulsar. Okay, so we talked about, well, star is pretty darn dense. You know, our star is pretty darn dense, but as it lives its life, the white dwarf, the retired star, is even more dense. And that's normal matter, though. A neutron star, basically electron degeneracy, has slipped, and now you have, what would we say, protons and electrons go to form neutrons. So now we have neutron degeneracy holding it up. In a black hole, nothing is holding up. It's kind of like a rip in fabric of space-time. So this is all to say that the black hole has, the singularity anyway, is the most dense material, and the star is the least dense material of all that stuff. Supernova type 1a, now do you remember what that involves? I'm going to go ahead and show you, refer to this figure up here. That actually involves your white dwarf and a swollen red giant again. But the difference here, and I double checked this is how it works. Basically, the matter that's dumped onto the retired star from the swollen red giant exceeds what we call the Chandrasekhar limit, exceeds that 1.4 solar masses. So it doesn't, nuclear fusion doesn't occur, but it's more of a slippage. The star, the white dwarf, collapses in on the weight because electron degeneracy can't support its weight anymore. So basically it turns into a neutron star, and it's that collapse that is kind of like the collapse at the end of a massive star as it ends its life. So it's that collapse and a kind of rebound, and anyway, it blows up, and I'm thinking then it leaves a neutron star in its wake. Not sure. Okay, so a supernova, a type 2 supernova, that would be the normal massive star blowing up. Remember, we said that would be 8 solar masses or greater. Gravitational redshift. Now that was, I don't know if you remember, I showed you a video where we had 2 spaceships. One was going to go near the event horizon. One was going to go near the event horizon. One was going to stay inside the event horizon, towards the singularity, and the other one's going to stay outside the event horizon. And as the one got closer and closer to the singularity itself, it actually became red, and it started out blue. And in this, in these notes here, what I've said is that gravity actually, the light needs to fight to get out of that, gravity. Okay, now I think I might be thinking of that wrong, but anyway, the light the light can still escape, but it has to lose some energy to escape, basically. And so it'll go from a blue color to a red color. Okay, black holes. So the blue thing in there is what we call singularity. The green around it is the event horizon. And the escape velocity then, if you are inside the event horizon, closer to the singularity point, then that means that your escape velocity, the speed you need to be going to escape the black hole, would have to be faster than the speed of light, or c, and nothing can go faster than the speed of light. So that's why you are just totally in trouble. So then we kind of switch gears from stars to galaxies, starting with the Milky Way galaxy. You're going to want to know kind of the general structure of the Milky Way galaxy. I don't know if you can tell, but kind of in the center there is a bar of stars. So we think it's a barred spiral galaxy. Let's see, the distance from left to right, or from the diameter basically, is about 100,000 light years side to side. We are about halfway out on one of the major arms, and so that puts us at about 25,000 light years from we call that the nuclear bulge in the center. That's kind of the group of stars. But the thing that's in the very center of our galaxy is the supermassive black hole. And we call that region Sagittarius A star. And I don't know, can't remember if this is a test question. I think it is. The reason we call it Sagittarius A star is because it's actually in the vicinity of the constellation Sagittarius. So kind of know the anatomy. The orbital motion of the disk stars versus the halo stars. The disk stars are nice and orderly, so our sun is what? Is it a disk or a halo star? Our sun is a disk star, nice and orderly. And then so they are more ordered, and then the halo stars are the wild children. They are more random. So in lecture, we looked at kind of these strips that look like the Milky Way, and the strips were different wavelengths. So we can actually see through what we call the interstellar dust, this dust between stars, in the plane of our galaxy by kind of looking. We can tease out the information. We can see past the dust by looking, changing our wavelengths. Okay, so down here at the bottom, I went ahead and make two columns for the disk stars and the halo stars. So for instance, if I were to ask you where are the old stars, hopefully you would say they are in the halo. If I were to ask you then which stars, old or new stars, generally have no heavy metals, hopefully you would say old stars don't have heavy metals because old stars aren't recycled stars. By the way, the old stars then, it's kind of backwards, we call the old stars population 2. And then we call the newer stars, the recycled stars, population 1, which is just kind of strange. Most stars are population 1. Our star is population 1. Okay, Sagittarius A star, like I said, that is actually where the supermassive black hole is located. And it's in the vicinity or in the direction of the constellation Sagittarius for us. And how do we know it's a supermassive black hole? Well, scientists can observe stars and dust orbiting this object, and this object has a certain, from its motion we can get its mass. And then from just its place in the sky, we can get its volume. So if you take that mass and you squeeze it into that particular volume, you have a density that reaches that where neutron degeneracy can't even support it. So it must collapse. The matter collapses in on itself and forms a black hole. So 3 types of galaxies. We're going to go with spiral, elliptical, and lenticular. And you're going to want to kind of know a description. Spiral will have the spiral arms. The elliptical are kind of spherical. Excuse me, or they could be elongated. Sorry. Lenticular are kind of these kind of irregular shapes. I think kind of a little disorganized is what I think. So we talked about that if you have a spiral or a barred spiral, then the more more tightly wound the arms, the more kind of fluffy or thick the nuclear bulge is. If the arms are nice and loose, then the bulge is thin. There's a test question on your test about that. So, okay, so Hubble in the 1920s, I just think this is so cool. We take for granted this idea that we understand the concept of a galaxy, and in the 1920s, but we don't. In the 1920s, we still don't know if those galaxies, those kind of wispy looking things, if they were a set of stars or was just like a nebula. And actually, in 1920, Hubble looked through a telescope at a distant Andromeda galaxy, and actually he could see a Cepheid variable star just kind of, doing its thing. And from its, we talked about this in class, you can use the Cepheid variable stars as a standard candle. So compared, using its period, knew its luminosity and compared its brightness with its luminosity to get distance. So that's what he did. He came up with the concept of a galaxy by recognizing Andromeda with that Cepheid variable. It was Andromeda galaxy, and it was 2.5 million light years away. I think that is so cool. So the next line there is actually something we talked about clear back in Unit 1, where we said light does not get to us instantaneously. There's a delay. Light takes a while to travel. Now, when we turn on a light bulb, you can't really tell that time, that sort of thing. But if an object is 1 light year away, then it takes 1 year for that light to get to you. And so we talked about then if you're looking at something, for instance, the Andromeda Galaxy, 2.5 million light years away, the light that we're seeing left 2.5 million years ago. So is that not cool or what? So we're seeing it as it was 2.5 million years ago. It's aged that much, okay? Standard candles then, like I said, the Cepheid variable that Hubble used was a standard candle. Standard candles are just great. They just mean that you know the luminosity. You know how much energy it's pumping out. And so you can compare how much you know it's pumping out to how bright it looks. And then you can get the dimming factor that the distance has created. Okay, so you can calculate distance. Hubble's law said that Hubble saw that all galaxies were moving away from us, and specifically, he said that the farther away the galaxy, the faster it was receding from us. It's like, that's nothing to take personal, right? And so if it's all moving away from us, you could kind of go backwards to a point when it was all together. And that's kind of the way it works for Hubble to estimate the age of the universe and the time when the universe was just very small. We'll talk about this in Unit 5. A point what we call singularity was what the universe was all packed into. Anyway, if you kind of go backwards, take the clock backwards, you get a date using Hubble's constant of 14 billion with a B years ago is when the Big Bang occurred. So our universe now is 14 billion years old. Isn't that cool? So this one, the recessional motion and the redshift, is kind of related to Hubble's law. Hubble sees that the galaxies are all moving away from us. Well, one of the things we know about things that are moving away from you is that you get this Doppler effect, the redshift. So basically, the faster it's moving away from you, the more the redshift. So we definitely can see that in the farther galaxies are moving faster away from us and they have a greater redshift. Okay. So the galaxies, they have not always looked as they look now. Actually, with what would we say, 14 billion years under our belt, our universe, the galaxies have kind of settled into something kind of a little more pretty, a little organized. Going back in time, you kind of see that they looked, what did I use the word here? Distorted. The shapes of the galaxies were more distorted in the past. And the last thing I see here is quasars. And quasars are the most energetic event I think that we've probably talked about so far. And it's thought that quasars occur as a black hole is feeding. Yep. So I think that should do it for you.